Okay. So I have done that, and I think it is doing the recording, right?
Yes, sir.
Okay.
It's not, yeah, it's ready.
Yes.
Thank you so much.
Yeah, no problem. Thanks a lot. And thanks for telling me that I should start the recording. Okay, so this is what I plan to do for in my next hour or plus. Okay, so coming back to our presentation here. So let's talk about the historical event. But before I talk about the historical events that have come to this particular stage, if somebody is an environmental enthusiast and does some kind of net browsing or looks at literature as to what all people are talking about, you'll see plenty of things that are there that people are talking about. Now, on the one hand, you will see newspaper coverage as well as media coverage wherein people talk about carbon dioxide emissions. At the same time, there are some people who are talking about sea level rising. And then there are people who talk about greenhouse gases, population explosion. And then there are people talking about global warming that is taking place. Now, these are all the effects or consequences of various things like greenhouse gases emissions, and then sea level rising or population explosion and global warming. So people at the same time are also talking about possible solutions for these particular problems. And in that particular context of looking at solutions for these particular problems, people talk about renewable energy and sustainability as part of the solution for these particular problems. And there you will see plenty of literature, right from people and media to governments and governing bodies talking about renewable energy and alternate resources for energy. At the same time, in the international section, you will see something which is historically the foundation for these sustainability platforms, something called as a Brundtland report. I'm not going to go into details of this, but what I would like to tell you people is that this formed the first basis for people in the world to start looking at what is greenhouse gases and then why the weather is changing or why pollution is taking place. How do we want to stop this and how do we go about it? So this is the first report which came out quite a while ago, almost 3 decades back, that became the starting point. And the most recent that you will all come across or you will have heard about is the so-called IPCC report or International Panel on Climate Change. And in this particular context, our contribution has been significant. And in fact, I think one of the persons, Dr. Pachauri, who is no more, was leading this IPCC effort, and it indeed got a Nobel Prize. Most of you might be aware of it. Now, if you look at various things that people are talking about, so on the one hand, people are talking about greenhouse gases and carbon dioxide emissions, and on the other side, people are talking about rules and regulations in the form of Kyoto Protocol and IPCC report, and people talk at the same time coming out with solutions in the form of renewable energy. All these are going around, and there are lots of things that are happening around. Now, how do we understand most of these things and how do we make sense of it and where do we go from here is what I will try to address in my brief presentation over here. Now, before I go to the specifics, some of the pictures I thought are very important for us to understand the gravity of the situation. Now, one of the photographs that I was able to take here or show here for you people is that it is a glacier in Argentina. It's called as a Los Glaciares National Park in Argentina. And you can see this particular glacier is getting broken off from the wall at the back, and then it's coming down and falling into the water. And this breaking of the glaciers or ice blocks happens because there is global warming taking place and the water is becoming hotter and it is cutting through this particular glaciers of ice and making it to break off from the glaciers or the hills and walls of the glaciers and then become part of the water. And these are the concerns that people say when they see such photographs that the water levels are rising and we'll all get submerged. So these are the concerns that people have when they see pictures like this. So that is one of the things which happens because of warming that is taking place. And the second very interesting photograph as far as I was concerned, when I came across this particular news article, this is Greenland, which is nothing but the Arctic Circle. There, most of the times it is completely frozen and you should have ice or solid water on which people tread along. And in this picture that you see here in the month of June, there was so much of melting that had taken place that the dogs which were pulling this particular sledge had to be walking on water and not exactly on ice. So that was because there was so much of warming or hot weather that had taken place, and that had led to ice melting. So this was all indications of warming that had taken place. So this actually, this Argentina is the ice that was melting, and then the Greenland is ice that was melting, which are extreme events in the weather. Then that led to these events that are taking place for that matter. Then the other extreme that is also taking place is that these wildfires. I'm sure a lot of you must have come across this, especially in the past couple of months. Places like California in the US experienced a great deal of forest fires. And this is not California in the US, but at the same, this is actually Sweden. And most of us associate Sweden as a country to be very cold, and people associate it with ice being there or snow being there in majority of the time in Sweden. But this is actually the thing that happened in the year 2018. So this particular photograph of the forest fires was taken in 19th July 2018. You can see a forest getting caught in the fire and then all the trees getting burnt. And this happened because of extreme dry weather, and that led to warming and heating and the forest catching fire in the summer season, which is very, very unusual. So these are all the indications of the climate change that is taking place. Now this particular photograph here, where I'm seeing or I'm showing a woman standing on either sides of the water, is very close to us. And this is in a place called Gabura in Bangladesh, wherein extreme rainfall that led to complete flooding, and the houses were all had to be submerged in water. And this took place in January 24th, 2019. And what happens is, because of this heavy rain, the seawater comes into the land and it converts all the good water into saline water. So when it gets converted into saline water, it's no more usable, or it cannot be consumed by humans without cleaning it up. So these are all another important effects of extreme events and heavy rainfall and the seawater getting flooded back into the living places. So these are all extreme events that have been happening for the past several years. And some of the pictures that I'm showing here are from very recent events that have taken place. Now, if you put together and then try to ask a question, what is actually happening? And is there any record of why these things are actually happening? So that's where I thought I would like to dwell a little bit into historical events of what has led to this particular situation in the current season. Now, if one wants to sit back and then ask the question, how and when did all this start? Now, this is a very interesting question, at least to me. I said, okay, now, is this a very recent phenomenon, or does it have a historical precedent, and is it catastrophic that it happened only now, or has it been happening so far that it has come to this particular stage today? Now, if you want to answer most of these particular questions, then it's very interesting to go back and see what has been the record as far as warming is concerned. Now, when you look back, actually speaking, it is quite interesting that these three great scientists, most of you must have heard of these three people: Joseph Fourier, John Tyndall, who was a physicist, and then Arrhenius, who is credited with a lot of interesting things that have taken place. These were the three people who actually started thinking about the so-called warming phenomenon. Or in other words, they were the people, or Fourier were the first person who actually said, okay, fine, why are some places hot and why are some places cold on Earth? And if he asked this particular question as to, if I typically look at what is the source of heat for the Earth, and then if I do a simple calculation, what comes out to be the temperature of the Earth that we are staying on to be. So he was the first person to ask this particular question and to do a simple calculation. Of course, what he observed was that the temperatures were higher. I'll tell you a little bit about that one. But then he was the one who formulated this particular problem of heating. Then once he did this formulation, these two people, John Tyndall and savant Arrhenius, these were the two people who came out with positive evidence to show that indeed it happens because of these particular reasons. And I'll tell you these particular reasons as to why the heating takes place or why the earth is got a temperature that we have in different places for that matter. Why does the earth have a particular temperature? So to answer that particular question, Fourier first said, okay, now the source of heat for the earth is primarily solar radiation. That means it is the sun's rays which is coming onto the earth, and then it is having a certain intensity. So that means the sun light travels all the way from the sun to the earth, and then if one looks at this particular power density, it's approximately 1360 watts per square meter is the power density received on Earth's surface. Now, if you take this into consideration, that this is the only source of energy or heat for the Earth, and then ask this particular question, is this sufficient to give a temperature that we experience currently? Now, if you do this particular heat balance, you will come across or you will find out that the Earth's temperature has to be 253 Kelvin or minus 20 degrees centigrade. Now, most of you people who have been hearing to me will realize that this is an extremely cold temperature and it is impossible for life to actually survive at this particular temperature. So we have to adapt, or we have to have a lot of different clothing or warm protections for us if the Earth's temperature happens to be minus 20 degrees centigrade. Now, if one looks at it, this is not very correct because there are certain things that happen to this particular Earth's temperature. Now, on the other hand, this is a calculation of finding out that the Earth's temperature has to be 253 Kelvin purely based on solar radiation that is reaching the Earth's surface. That works out to minus 20 degrees Celsius. But then if you do an actual measurement of the Earth's surface temperature, then you will find that the temperature is somewhere close to 288 Kelvin. Or in other words, it's about 15 degrees Celsius. It's not very hot, but it's not cold either, like minus 20 degrees centigrade. But the average Earth's temperature comes out to be 15 degrees centigrade. So in other words, there is something like 35 degrees centigrade change between what is predicted or what is expected purely from the solar radiation that reaches the Earth's surface and what we experience as the temperature on the Earth that we are living on. So there is a 35 degrees centigrade which needs to be understood or explained. And this particular explanation was given actually by these two people, John Tyndall and Arrhenius, as to why this difference in the temperature to the extent of 35 degrees comes about, or what is the source of this extra heat that is present on the Earth that gives rise to this warmer temperatures than what is expected. But in other words, if you look at this particular data of minus 20 degrees centigrade and 15 degrees centigrade, you will find that it is hotter than expected. Of course, it is extremely good because we know that it is extremely difficult to survive at a temperature of minus 20 degrees centigrade, but it's relatively much comfortable for us to survive at a temperature of 15 degrees centigrade. So it's a welcome change from a cold temperature to a hot temperature. So hotter than expected is much absolutely welcome for warm species like us to survive on this Earth, but we have to understand what is the source of this particular heat or the comfortable temperatures that we experience on the Earth's surface. Now, when you look at this and then look at our atmosphere, what happens is there are plenty of plants and animals and various types of creatures that are present on this Earth's surface. Now, if you look at it, there are two gases. I would consider even water as a gas because it is present in the atmosphere. So there is carbon dioxide and there is water which is present in the Earth's atmosphere due to the various activities that are being conducted by the species that are existing on the Earth's surface. So the plants, the animals, the insects, the human beings, everything that is present on the Earth has a certain activity that results in producing carbon dioxide, and it also leads to certain amount of water getting evaporated into the Earth's atmosphere. So what happens beautifully is that the solar radiation that comes onto the Earth's surface, part of it gets reflected, which we generally nowadays call it as infrared radiation or IR for that matter. And this particular long wavelength radiation actually gets reflected from the Earth's surface, but it doesn't go back to the space, but it gets absorbed by these water and carbon dioxide molecules that are present in the atmosphere. Now, Arrhenius and then Tyndall did beautiful experiments to show that even tiny quantities of carbon dioxide and water vapor present in the Earth's atmosphere act as insulating covers. They're insulating covers because they absorb this infrared radiation and then radiate it back onto the Earth's surface. So as a result, they sort of trap the heat or keep that infrared radiation trapped in those molecules and re-radiate that particular heat. And this particular heat or infrared radiation that is given out by carbon dioxide and water molecules that are present in the atmosphere ends up heating the Earth's surface further compared to solar radiation purely. Or in other words, that 35 degrees centigrade difference that we saw earlier is because this infrared radiation that is reflected by the carbon dioxide and water molecules that are present in the Earth's atmosphere ends up coming back to the Earth and then heating the Earth's surface. And that leads to essentially defreezing many parts of the Earth. Carbon dioxide and water in the atmosphere are essential to keep the Earth from freezing. See, right in the beginning, I showed you a particular slide wherein people talk about emissions like carbon dioxide, which are very bad. You know, this is a general feeling that everybody gives to us. And if you read any media or if you sort of browse the internet, everybody says carbon dioxide emissions are bad and we have to control them and we have to reduce or bring down the carbon dioxide emissions. But at the same time, one has to remember that carbon dioxide and water vapor are absolutely essential to be present in the atmosphere so that we have a comfortable temperature to live on the Earth and not freezing cold weathers. That's extremely important. And I'll come back to this particular point of emissions or carbon dioxide a little later again as to why people talk about these carbon dioxide in the atmosphere being bad. Okay, so for the time being, please understand that carbon dioxide is not a villain in the piece or not a demon in the atmosphere, but it is absolutely essential and required. How much is required? What is required? We will talk about that particular fact. But the point at the moment to remember is that carbon dioxide and water vapor are absolutely essential to be present in the Earth's atmosphere. And if they are not present, or if we completely take the carbon dioxide out of the atmosphere, then the Earth's temperature will drop and it will become freezing cold and it will become extremely difficult for many of us to survive on the Earth. Okay, so remember this particular fact. So what I'm trying to say as a summary of this particular discussion is that the Earth's temperature, if carbon dioxide and water would not be there, would be freezing cold at minus 20 degrees centigrade. Okay, but because thanks to the presence of carbon dioxide and water vapor in the atmosphere, we are having a comfortable 15 degrees centigrade temperature. Okay, so this is one of the nice images that I could come across, which is an infrared radiation image that was taken by one of the satellite probes. So what this particular photograph shows is that the temperature distribution over the Earth's surface. So if you see the globe, and then if you say, okay, fine, I'm going to map the temperature contours of this particular globe right from top, that is the Arctic to the Antarctic, and say, okay, fine, how does the temperature get distributed, or what is the distribution of temperature across the various parts of the globe, you'll find that on the top where you have the Arctic, it has pretty cold temperatures, which is given in blue color, and at the bottom, which is Antarctic or the South Pole for that matter, again, it is extremely cold. And in the middle, we have these hot bands or these equatorial regions, which are quite hot. And many of these places have got deserts as well, because of which the temperatures goes up. Or in other words, if you look at the temperature distribution, it can go anywhere from minus 81 degrees centigrade down in the South Pole to 47 degrees centigrade in the equatorial regions of the deserts, wherein you have extremely high weather, high temperatures. Now, if you take an average over all these particular temperatures of the Earth's surface, then it comes out to about 15 degrees centigrade under normal circumstances or normal conditions. So this shows the distribution of the temperature across various parts of the globe, And please remember, it can go anywhere from minus 81 degrees centigrade to plus 47 degrees centigrade, with an average about 15 or 20 degrees centigrade for that matter, which is an average Earth's temperature. So this is what our Earth, purely in terms of temperature, looks like. We have hot regions and we have extremely cold regions. Now the point is, historically, I was talking about carbon dioxide. The carbon dioxide levels in the atmosphere have been somewhere in the range of 200 ppm to 280 ppm for thousands of years. And this is extremely important for most of us to remember, okay? Now, when I said earlier, people like Arrhenius and John Tyndall did experiments to find out the role of carbon dioxide in the Earth's atmosphere, or what is the nature of absorption of the various parts of the solar spectrum or energy by these molecules like carbon dioxide and water. They found that even small quantities, remember 200 ppm is not a very, very big concentration of carbon dioxide in the Earth's atmosphere. So concentrations like 200 ppm to 280 ppm on an average for thousands of years was existing in the Earth's atmosphere, and that's what gave us that particular temperature distributions for that matter. So this is the carbon dioxide levels which was present historically 200 to 280 ppm for thousands of years. Now, like I said, this is important because people could survive on the Earth's surface without having to have too much of cold weather related problems, because this presence of 200 to 280 ppm carbon dioxide in the Earth's atmosphere warmed up the Earth and led to the Earth's average temperature being about 15 degrees centigrade. Now the question comes is, why is everybody talking about carbon dioxide being a bad actor or a villain in the piece for the Earth's atmosphere? Now, if you again look at historical data of carbon dioxide and various other gases which are considered to be equivalent to carbon dioxide in terms of absorption of the radiation and emission of the radiation again, then you will find that these carbon dioxide levels from the historical levels of 200 to 280 ppm, which were there in the 1700s or so, have started to gradually increase. Now we see here, the black curve is carbon dioxide, and there is something called greenhouse gases, which are not exactly carbon dioxide, but they have the same or similar effect to that of carbon dioxide. Now, if you see that the concentration of these particular gases has been steadily increasing rather exponentially or somewhat exponentially with respect to time. And you see carbon dioxide alone, which is given in sort of bluish color over here, it was pretty stable for a long, long period of time, like thousands of years. And then around 1700s and 1800s, it starts to deviate, or in other words, it starts to dramatically increase or rise with respect to time. And this is actual experimental data or observations by the National Institute of Atmospheric Sciences in the US. Okay, so this is actual data. So the carbon dioxide levels have gone up from 200 ppm or 280 ppm approximately so to about 400 ppm at the current level. So if you see here, there is a 200 ppm increase or almost doubling of the carbon dioxide concentration in the Earth's atmosphere. And this dramatic change or very significant change in the carbon dioxide concentrations took place around this period of time, somewhere around the 1800s. And I'll come back to this particular point of what is significant around 1800s. Now, if you see this, around 1800s, there is a dramatic change in the carbon dioxide levels. Then we have to try and understand what actually led to this particular change in the carbon dioxide. Okay, now if you convert the carbon dioxide in the atmosphere to temperature differences, because remember, when there is 200 or 280 ppm carbon dioxide in the Earth's atmosphere, that results in a certain average temperature for the Earth. And then if you say, now my carbon dioxide levels are going up from 200 or 250 ppm to about 400 ppm at the current stage, then the Earth's temperature is an indicator of this carbon dioxide concentration in the atmosphere, and the heating effect is going to be going up because the carbon dioxide presence in the atmosphere leads to more and more infrared radiation from the sun's rays to be caught and trapped and then given back to the earth for heating it up. So in other words, if you say, okay, fine, what is my earth's temperature and how is it changing with respect to time, you will find that the difference between the average and the actual temperature again start to increase at this particular point of time. Somewhere around 18 to 1900s, there is a gradual change, and then after 1900s, there is absolutely a positive trend of increase, or the difference between historical average and the current temperature keeps on rising with respect to temperature. So these are actual temperature difference data that has been collected over centuries for that matter, and then plotted as difference temperature. And from different regions in the earth, when people collect this data, they found that there is absolute agreement of differences in the temperature between what is historically an average temperature and the current temperature. It absolutely matches. You can see all these different curves of different colors matching exactly or more or less overlapping or simply falling on each other, which says that yes, there is an absolutely confirmed trend of increasing Earth's temperature. So that is what has actually happened. Now, the question is, what is so significant about 1800 AD? Now, what actually happened around 1800 AD that the carbon dioxide levels in the Earth's atmosphere started to increase, and as a result of the increase in the carbon dioxide levels, the Earth's temperature also started to increase. Now, if we go back and try to understand what led to this particular change, the biggest thing that has happened is that the invention of steam engine, or in other words, the coal being used as a source of heat or energy. So which is what I'm trying to call here as fossil fuels being used for generating or having a control on the heat that is there, or we could harness energy, or we could shape the energy to whatever use we could put together by using these fossil fuels. That was the biggest dramatic change that happened around 1800s for that matter. And this actually led to what we call in modern language, the Industrial Revolution. Okay, now first and the foremost that happened is that people found out that coal could be burned and converted into a usable form of energy, and that particular usable form of energy could be used to perform various activities. And the first and the foremost activity that was performed using this energy that was locked up in the coal was, of course, running these so-called steam engines for that matter. So that led to Industrial Revolution. And what is the consequence of Industrial Revolution? And this is what is a so-called picture, wherein I'm just showing a lot of stacks or exhaust chimneys that are coming from various industrial activities, and then they releasing certain gases into the atmosphere. So in other words, around 1800, humanity could learn to access and harness the fossil energy that is locked up in the fossil fuels, and then harness that to do various activities. So now somebody might say, okay, that was good because it was a positive step that led to Industrial Revolution and people having a lot more energy to do a lot of different activities so that we could advance or progress from our ancestors to current day civilization or current day population with a lot of so-called quote unquote progress that has taken place. Because nothing comes free, and there are a lot of things that happened as a result of this particular invention or being able to harness the energy that is present in the fossil fuels. Now, what happened when again, if somebody does a simple calculation, then you'll find that in the biosphere, I told you right in the beginning, there is a carbon dioxide because there is plants and animals and human beings that are existing on the Earth's surface, and all human activity and the plant activity result in generating certain carbon dioxide. Okay. Now this particular carbon dioxide is in a cyclic fashion, which we call as carbon cycle or carbon dioxide cycle of the Earth. In other words, what happens is the carbon dioxide that is present in the atmosphere is a result of a delicate balance between human beings, animals, life forms, and the plants and the oceans that are present on the Earth's surface. And without going into the details of this, which people call it as a biosphere or the carbon dioxide cycle of the earth, then if somebody does a simple calculation of how much of carbon dioxide is being circulated every year by the so-called biosphere, or the animals and the plants and the human beings and the oceans or the waters that are present on the land, okay, it works out to about 440 gigatons. Okay, please remember this number is very important. So the biosphere or the land-based activity results in circulating or keeping in balance 440 gigatons of carbon dioxide. And then there is an equal activity of carbon dioxide that goes through the ocean water and then comes out from the ocean water. And if you take that particular carbon dioxide, which is cycled through the water media, and it is about 330 gigatons. Or in other words, if you put together the total quantity, it's about 770 gigatons of carbon dioxide every year is circulated in the natural cycle of the biosphere. In other words, the humans and the plants and the animals are part of this particular circulation, and then they circulate every year 770 gigatons of carbon dioxide. It's a perfectly cyclical system that goes through. Then the question that one would ask, if you look at these particular numbers, is that, okay, we talked about industrial revolution, and these industrial revolution has learned, or human beings have learned, to use the fossil fuels and convert that fossil fuels into usable forms of energy. And in order to convert that fossil fuels into usable forms of energy, we also result in producing carbon dioxide. So this is what we call as industrial activity related carbon dioxide emissions into the atmosphere. Again, it's not very difficult. People have done these particular calculations over a period of time, and a lot of people have looked at this particular problem. And what they find is that the carbon dioxide emissions from fossil fuel burning, okay, all this coal, gas, oil, that are fossil fuels, and if you take it and then burn it in order to gain energy, or the calorific value that is present in these fossil fuels, the amount of carbon dioxide that is generated is about 26 gigatons. Again, please pay attention, or please note the fact that the human activity of fossil fuel burning leads to approximately 26 gigatons of carbon dioxide being generated by the humans or life form on Earth. And if you compare that with respect to the natural cycle of carbon dioxide, or the carbon dioxide cycle, it's about 770 gigatons. So if you do a simple calculation and find out what does it constitute, it's just about 3.4% of the total carbon dioxide that is involved in the natural cycle. Okay, so 3.4% of total carbon dioxide of the cycle is generated by the human activity or earthly activities of fossil fuel burning. So the question is, there are lots of people who will ask this particular question. 3.4% or 26 gigatons compared to 770 gigatons is nothing. It's a small quantity. So why make such a big fuss about carbon dioxide emissions? That's a very important or a pertinent question, because when you compare the natural cycle with respect to human emissions, it is just about 3.4% of extra carbon dioxide that is generated by the activity on Earth. Now, in order to show you the impact of these 26 gigatons, I would like to take a simple chemical reaction approach. And I hope most of you in the audience who is listening to me would have knowledge of the simple chemical reactions or chemical balances. It's not very complicated. It's an absolute simple balance is what I'm going to use as an example to illustrate the importance of these 26 gigatons. Now, if you take this, the natural carbon dioxide cycle is an equilibrium process, because every year there is generation and consumption that takes place. Or in other words, if you put it in terms of a chemical reaction, there is A plus B, which is generating carbon dioxide and producing C plus D. And this C plus D, in other words, consumes this carbon dioxide, and it is a cyclical reaction that goes forward and backward. And as a result, there is a net balance in the carbon dioxide. Okay, that is involved in this cyclical process of natural cycling. Now, if you look at it as an chemical reaction or an equilibrium reaction, because it's a cyclical reaction that is taking place, then this cyclical process has a rate constant like that of a chemical reaction. Every chemical reaction, all of us know, has got a rate constant. Now, the point is, if there is a small change in either the reactants or the products, then the rate of the chemical reaction gets upset and the chemical reaction gets completely biased one way or the other. So for example, if there is a change in the A plus B or the reactants on one side, which is the left-hand side here, then the reaction gets biased towards C plus D in order to keep a balance. And the same thing happens in the opposite direction. So if there is a change in the C plus D, even by a small quantity, then the reaction balance changes and the rate constant changes, and in turn, it affects A plus B. Okay, I hope all of you will agree to my particular logic, saying that even a small change in A plus B or C plus D will upset or change the reaction balance and then drive it towards one direction or the other, either towards A plus B or towards C plus D. In an absolutely identical fashion, what happens is the gases that are emitted into the atmosphere, and I'm bringing in more gases into discussion over here. I was talking about only carbon dioxide earlier. So the greenhouse gases, or all the gases which have the potential to absorb the infrared radiation that is coming from the Earth's surface, that includes methane, nitrous oxide, then chlorofluorocarbons, and various other gases that are there, which are generally clubbed as greenhouse gases, or Gs for that matter. What happens is, if there is a small change, remember I said 26 gigatons. So no matter what is the amount of these changes in the concentrations of the greenhouse gases, the reaction gets upset, or the natural carbon dioxide cycle of equilibrium gets upset. Now what happens, like this reaction rate constant, it has a certain amount of balance. Now if you bring in too drastic changes in the concentration of either C plus D or A plus D, the reaction goes uncontrolled. And most of you probably know this. Once the reaction is uncontrolled, then it leads to very bad or very unwanted consequences. In an absolutely identical fashion, what happens is this natural cycle or the biosphere has got a capacity to take these extra carbon dioxide that is released by the human activity. I would like to call this as human activity. Now, what happens is, if this amount of carbon dioxide that is left, or greenhouse gases that are left into the atmosphere, goes beyond the capacity of the Earth to manage it, then it leads to unwanted consequences, or in our case, drastic events or extreme events, like the photographs that I showed you earlier, wherein the glaciers were melting and the Arctic ice was melting, or in other words, there was extremely huge amount of rainfall which leads to flooding, and then backflow of the seawater into the river water to cause salinity, or for that matter, extremely dry weather like that of the Sweden case, wherein forests were getting caught in the fire and the trees were getting destroyed. Or in other words, this leads to insulating blanket around the Earth, these greenhouse gases, and they trap more and more heat onto the Earth's surface, and that leads to global warming. Okay, so to summarize the historical events, what you see is that the nature had kept things in balance for centuries or for thousands of years, maintaining a natural carbon dioxide cycle to have somewhere around 250 ppm carbon dioxide in the atmosphere that was sufficient to keep the Earth's temperature around 15 as an average temperature. But the industrial activity or the industrial revolution, or harnessing the fossil fuel energy, led to industrialization, and that led to increasing amount of carbon dioxide into the atmosphere. Now you can realize the impact of what I was trying to tell you, hopefully. Now, although 26 gigatons is released per year, what happens is if this 26 gigatons is not consumed or neutralized by the natural carbon dioxide cycle, some amount of this particular 26 gigatons is going to be left behind, and it is cumulative. So year on year, it gets accumulated. And that's the reason why when I showed you this carbon dioxide increase graph here, you see that the accumulated carbon dioxide keeps on increasing with respect to time, because not all the amount of carbon dioxide or greenhouse gases that are emitted into the atmosphere are being digested or neutralized by the natural cycle of carbon dioxide of the biosphere, and there is a residual effect which is accumulative, and there is a buildup of carbon dioxide in the Earth's atmosphere. And this buildup leads to greening or heating of the Earth's atmosphere, which leads to a lot of these unforeseen events or global warming for that matter. Now, this is all about global warming. Now, the question somebody at this particular point has every right to ask me is, sir, you told me, or your title of the talk was materials. So where are you headed with this particular concept of global warming? And then how is it related to materials? Or in other words, how do materials fit into this particular story that I'm trying to weave or tell you that there is global warming that has taken place? And in order to actually illustrate the role of materials, I will take a couple of examples here. Okay. Now, if you can notice here, most of you people might recognize this particular photograph that I'm showing you here. This is nothing but a book with all its pages being flipped open, or they're being displayed like a fan. Now, if somebody just sits back and thinks about it, it is very interesting, because although we treat it as a simple book, there are almost 10 different types of materials that are present in that book. So there is a paper which is there is ink, and there are different types of inks and colored inks, and then there is something that is used for binding. Even if you take thread or a cotton that is used to bind all the papers into a book. So like that, if you count every material that is present in a simple thing like a book for that matter, there are 10 different materials that are present in each book, or in a single book for that matter. Or in other words, what I'm trying to illustrate is that even a simple thing like a book has got 10 different materials are required in order to make this particular book. Okay. Now, if you look, sorry for this particular slide, it is sort of turned upside down, not upside down, in a 90 degrees turn, but I'm sure you will all be able to appreciate this particular figure. And I'll tell you what this particular figure is. Now, what is being shown in this particular figure is materials with respect to historical time. So it goes to 100,000 BCE or before Christ to the present date, like 2020 for that matter. Okay. Now, if you see historically, what has happened is that all of us have learned as part of history is that we had age of natural materials, and then we had the dark ages, then we have what is called as age of polymers and age of composites, and then age of what we currently call as functional materials. Or in other words, if you see the bottom of this particular slide, we have all learned in school for that matter that human beings have evolved from what is called as stone age, and then copper age, bronze age, iron age of steel, age of silicon, and then currently we are talking about nanotechnology and molecular age or atomic age for that matter. So what I'm trying to show here in this particular figure or in this particular photograph is that the evolution of the human species on Earth is directly linked or directly correlated with materials. And that is illustrated at the bottom. So the ancestors for that matter, people who were living like 100,000 years ago, they were called as Stone Age people, and they were using only stone for their daily activities. And as they become smart, quote unquote smart, they started to realize the use of copper, and then they started to realize the use of another material called bronze, and then subsequently iron and steel and so on and so forth. Then what has happened is people have undergone, or humanity has undergone change, okay, or developments that have seen. So all these developments historically have coincided with discovery of realization of use of a certain material. So stone is one type of material, copper is another type of material, bronze is another type of alloy, pure iron is another form of alloy, steel and silicon, which is used on our so-called information technology, and then now we are talking about nanotechnology. Or in other words, there is an absolute direct correlation between human evolution and change in the materials that are being used by the humans for various activities. Okay, so that's what it is. Now, if you see this, what happens is, if you see at the bottom or at the Stone Age, there are long time steps that are there at the bottom of that particular graph. So with the advent of human beings, or with the ability of the human beings to be able to harness the energy that is present in the fossil fuels, or the calorific value, convert that calorific value into energy, there has been rapid changes in technology or rapid changes in materials consumption. So we went from Stone Age to Copper Age to Bronze Age, all that to Iron Age and Steel Age. It took centuries for the human beings to go from Stone Age to Steel Age, for that matter. Then what happens? The moment you come to Steel Age, after that, the time gap between development has started to decrease. Or in other words, from steel to silicon to molecular age, the maturity of the technology or the materials usage has become shorter and shorter. Or in other words, what has happened is we have gone at technological developments which have got shorter and shorter lifespans. All that is because we have learned the art of materials consumption, or exploiting the materials for our different activities, for that matter. And then if you compare it at the moment, the current global consumption of materials is about 1.4 tons per person per year. Remember, this is a huge number, especially if you sort of translate this particular number into human population. It comes to 10 billion tons of material, one form or the other, is used by humans every year. Or in other words, we are producing and we are consuming 10 billion tons of different types of materials every year for various activities. Now, if you compare it with history, the hunter-gatherer or a Stone Age person was just using 0.5 to 1 ton per annum, okay, for their daily living. Then if you come to the agricultural society, or when we started to use the land and start to grow crops for our consumption, then the amount of materials that were consumed went up from 0.5 to 1 ton to 3 to 6 tons per annum. So we increased it by 3 to 6 times the amount of material that is consumed by human being per year, for that matter. Then the so-called industrial technology, industrial revolution came up, and then our activities became larger and larger. Our materials consumption has really increased great deal after that. So you can see in the industrial age, we are consuming materials at the rate of 15 to 40 tons per annum. Okay, so this is the average consumption, or in most of the industrial activities, we are consuming 15 to 40 tons per annum. Now, this 1.4 tons per person per year is because there are plenty of poor countries which are consuming much less compared to advanced countries. So if you take a typically advanced or so-called industrialist countries, they're consuming anywhere from 15 to 40 tons per annum, and it can range anywhere from 15 to 40 tons to about 1.4 tons per person per year. So there is a significant increase in the materials consumption because we are able to master the art of materials consumption with respect to harnessing our energy, or using the fossil fuels for energy and using that energy for converting various materials and using various materials, for that matter. Now, what is happening? If you currently look at this, this is data in the late 20th century, or for that matter, 21st century. This is, I think, if I remember correctly, this is 2014 or 2015 data. You see the annual world production, if you see steel or concrete or asphalt or cement, or even wood for that matter, it runs to billions of tons per year is the materials consumption. So we are consuming all the different materials, metals or alloys, polymers, ceramics, and various other types of materials, including woods, in the order of millions to billions of tons per year. So there is a huge materials consumption that is taking place, which is because of industrial revolution that has taken place. Okay, so this is the significant numbers of materials consumption. Now, the crucial role of materials and how humans have depended on these materials, I will illustrate with these two examples, okay, which are very interesting and which is most easy for most of you to follow. I don't think it will be too difficult for anybody to follow as a result of or as a function of time. Now, if somebody looks at communication device, which we call as a telephone, and these days we call it as a mobile phone, there has been a sea change. Okay, now I'll show you because most of the audience would not have seen this earlier version of a communication device because it was 40, 50 years ago, and many of you would have born after these instruments were faded out. But of course, in India, we still use many of these devices. Okay, now if you see the conventional telephone or a communication device, it looks something like this. Okay, so this is a device which was in 50s and 60s, very predominantly used, and still in a lot of the developing countries, this kind of instrument is still being used. It's not completely gone or outdated for that matter. So we still use this kind of a device. But then there is an increasingly larger number of communication devices which have gone a change from this type of telephone looking to this handheld device. And of course, I've taken this particular photograph of Samsung. It is no reflection, and I'm just showing it as an example. And I'm not a brand ambassador for any particular brand for that matter. So please take it that we have gone from using this telephone as a communication device to using this mobile phone as a communication device. So somebody can say, what's a big deal? It's a great tool or a great device because we are able to not only call, but we are able to take photographs, transmit photographs, and then have these online communications and chats using this particular type of device. Absolutely perfect. There's a technological development that has taken place by going from these red colored telephones, which are absolutely simple and only voice enabled devices, to devices which are enabling not just voice, but even pictures and live photographs for that matter. Great. Okay. So there's a lot of change in the technology that has taken place from these earlier devices of 40s and 50s to present day communication devices. What does it mean in terms of materials? Because I'm a materials person, I would like to look at it from a materials perspective. Now, if you look at it purely from a materials perspective and say, okay, fine, I'm going to present or rather project my materials with respect to the periodic table that we all know, then you find that an instrument like this, which was a communications device in the 40s and the 50s, depended or required only these highlighted elements. So you can see hydrogen, chromium, iron, nickel, copper, zinc, aluminum, carbon, nitrogen, oxygen, tin, and lead. So these were the elements in the periodic table which were required in order to make this absolutely simple, only voice-enabled communication device, which is the telephone of the 1950s. So if you take this and then you say, okay, fine, what is it that I'm trying to focus here on? The color of these particular elements, and 12 elements from the periodic table were required in order to make this particular telephone. And these 12 elements from the periodic table ranged from polymers to alloys. Elements like carbon, hydrogen, nitrogen, and oxygen, which were used to make polymer body or a wire for that matter, to some of the internal stuff which is made of alloy systems. So wherein you used iron, chromium, nickel, and copper and zinc kind of an element. So totally, all in all, there were just 12 elements which were required in order to make this particular communication device. Now, this is where the surprise comes, at least to me. I hope it's a surprise for all of you too. Okay, now if you say, I'm going to compare the materials intensity of my modern day communications device, then you will say, okay, fine, what are all the different elements in the periodic table that are absolutely essential in the current mobile technology? You'll find that apart from those elements, the 12 elements that were used in the earlier versions of the communication device, you'll find that there are plenty of other devices also, other elements also, which are absolutely required. On top of it, you'll find that in the previous periodic table that I showed you, there were only yellow colored elements. Now, on top of the yellow colored elements, we have also got several other elements in the periodic table, which are all colored red in this particular figure that I'm showing here. Why am I coloring red? So what happens is, if you compare it with the earlier instrument, there were only yellow colored elements, and we have added more number of elements from the periodic table. And if you count the total number of elements, there are 34 elements which are there in the periodic table, which are absolutely essential or required in order to make this communication device or a mobile phone for that matter. Okay, now the yellows are 34 and the reds are 21 red colored elements which are required. And these are crucial or critical elements which you will find that they're not easy to get by. So if you see from the periodic table or from the earlier version of the telephone, we needed 12 elements and none of them were red or critical. Now, if you see the present day device, there are 34 yellow elements. We have gone from 12 to 34, and on top of it, we have added 21 red colored elements, which are not easy or critical elements for you to get by. Or in other words, if you want to make a mobile telephone, 40% of the red colored elements are required, or which are very critical elements. What I'm trying to tell you, I'll show you another example and then I'll try to summarize what happens. Then another extreme example that I thought is interesting for us to talk about is the transportation vehicle. Now, if you see the earlier version of the aircraft, then that looked something like this, a commercial airplane, and then that went into a lot of technological changes. And then the current day transportation vehicle looks like this. So the aeroplane, which was looking like this, became modified because we had access to technology and of course materials, and that has got transformed to an aircraft that looks like this in the present day period. Now, what does it actually mean? Now, again, if we project it onto our periodic table, then the conventional aircraft, which we call as a turboprop aircraft engine, just the engine, mind you, it required these elements to be made. The engine consisted of elements which are made of these elements, okay? And there was only one element, tungsten and so-called iridium, which were required to make this engine, which was required for that aircraft. So there are 8 elements which are yellow colored, which are easy to get, and then one element which is critical, that is a red colored element. So there is only about approximately 10% criticality in the elements that are required to make an aircraft engine. Now, if you look at it in the current day turbo engine or a jet aircraft, and then look at the engine that is required for these fast flying aircrafts that we use these days for our transportation, you will find that elements has gone up from 16 to now 16 plus 9, that is 25 elements compared to only 9 elements that are required in the periodic table in the earlier version of the aircraft engine. Now here, what has happened is not just yellow, we have added red elements also, which are considered crucial or critical, or in other words, we have become 36% critical when we talk about a transportation, present day transportation aircraft engine, which actually means that we have gone from using less number of simple elements in the periodic table to make things. We have advanced in technology, all right, but at the same time, we have become very much dependent on availability of materials, not just availability of materials, but we have diversified or expanded the use of our materials, and we are not limiting to just a few elements in the periodic table. We are using almost every element in the periodic table. And that is really clear if you see the mobile, okay? So I'm just trying to go back to that same figure again to tell you that if you see this, the mobile uses almost every element in the periodic table. So there is 55 elements that are present in the periodic table that are required in order to take the mobile phone. In other words, we have added extra facilities to the mobile telephone, but at the same time, we have become extremely vulnerable because we require 55 elements to make this particular mobile phone. So our dependency on materials has significantly increased compared to earlier times wherein we were using very few elements. Now, what does it actually translate to? Again, I'm showing a 90 degrees turned slide over here. In the earlier age, where we were talking about hunter-gatherer, where people were using implements like stone, or even for that matter, copper or brass or iron for that matter, most of it was recyclable. Or in other words, there were materials that were consumed for their daily activities were renewable. You know, even if you take steel for that matter, majority of the steel could be recycled back after it has finished its life and then used again. So gradually, with respect to technology development and materials development, we have gone from 100% renewable materials consumption to a drastic change to become totally non-renewable materials consumption. So if you see this particular red curve, which is shown here, we have gone from 0% non-renewable or 100% renewable to 100% non-renewable or nearly zero renewability. Or in other words, we have gone from a stage wherein we could recycle our materials to a stage wherein we have completely gone away from that recycling concept to 100% non-recycling concept. Now here, if you see this, actually speaking, materials have become building blocks of technology. With the two simple examples that I showed you, is that there is technological development and there are materials that are required for this technological development. Okay, they're absolutely crucial, and no technology is implementable without real availability of materials. So although we do talk about communication and all these modern day devices, none of those devices are practical or realizable, or the concepts are realizable without the usage of materials. So materials actually are absolutely a solution, or in other words, they're a gift, and at the same time, they're a curse as well. So the materials are no doubt a solution for our technology development or realizing our technology, but at the same time, they're also significant problem creators, because we have gone from an age of using completely renewable materials to completely non-renewable materials, wherein they become a big problem for us to look at. And that becomes clear in a way. Now, what has happened? Like I said before, what exactly are the reasons for this? So if you look at this, what has happened in earlier times, we were having completely renewable materials. That means we were using it in a cyclic fashion. And then we have come to the 21st century, wherein we have come to a linear model of using the materials. Or in other words, we have got this linear model of take raw materials from the earth, convert them into usable stuff, and then sell them or use these particular materials and then dispose them. And this is what is traditionally, or these days, is called as a linear materials consumption model or linear model of development. Okay, we have gone from a cyclic model to a linear model. And this we call it as growth, because we say we have gone from a simple telephone or a dialing telephone to a mobile phone or a touchscreen mobile telephone or a turboprop aircraft engine to a jet engine for that matter. All this so-called growth has come about because materials and energy consumption have taken a drastic change, or we have changed our consumption pattern of materials and exploiting the materials, and that has facilitated our technological development, and that has also spoiled us in adapting this model of take, make, use, and dispose, which is an absolutely linear, non-sustainable model. Now, there are a lot of pitfalls for this particular approach of linear modeling or linear consumption pattern. Now, pitfalls of this approach: it exploits natural resources for present day needs only. And then the future generations and other forms of life are not at all a factor to be considered. Okay, so we just use it for the present, and then we consume all the materials and we throw away without considering the fact that once we convert these particular materials, they've not gone back to the original form and they've become useless for the next generation of people for that matter. So in the current model, we prioritize wealth and ownership of goods. Okay, so this is the so-called growth model that we have been accustomed to or we are using at the moment, which results in this linear model of consumption. Now here we are equating growth to prosperity to inflation, which I think personally are not the correct way of analyzing or looking at things. Okay, so when you look at this, the natural resources are not inherited but borrowed from future generations is what one needs to be considering or factoring when we talk about materials consumption. So I'll sort of go a little bit faster here now. Okay, now the effects of technology-based development model, degradation of air, water and land, which we have seen as a consequence and leading to extreme weather events, loss of biodiversity, resource depletion, and then social inequalities are also coming. Then the first three are environmental effects, the social inequalities or societal concept that we have. Now, before I go into specific examples, I quickly want to run through two extremely important parameters that most of the materials developers or modelers or designers have completely ignored so far, which has led to this non-sustainable growth or non-sustainable consumption patterns. Now here, the first parameter or the first concept that I would like to talk about is something called as embodied energy. This is extremely important, and this particular embodied energy is defined as energy or equivalently carbon dioxide equivalent, but you don't have to worry about this carbon dioxide equivalent, but just think of it as energy. Now, this particular energy includes various forms of energy that are part of the material or the product system. And it includes both recoverable or renewable part and a non-recoverable part. Okay, there are two components to it. One is recoverable and the other cannot be recovered at all. So that is included in this embodied energy. And this particular concept of embodied energy can be applied to anything. It can be applied to a material. It can be applied to a building that the Shunya team is trying to build, a house. So when you're trying to build a house, it is extremely important for us to keep in mind that there is something called as embodied energy, which needs to be accounted for or factored when we are designing house or when we are designing a building to say that this is sustainable for that matter. So you can extend this particular concept of embodied energy from materials to commodities to buildings. There is absolutely nothing restrictive about this particular concept, and it is quite universal or broad-based. Now, this embodied energy is not a constant. It can change with changes in technology or raw materials usage. Okay, I don't want to delve into this particular example here, 100 tons of wood. I'll just cite this particular case as an example. So if you just think about the fact that steel or iron is basically present in the Earth's atmosphere or land as iron ore, the iron ore had to be converted or iron oxide has to be reduced to iron. Or in other words, this conversion process of iron oxide into iron thermodynamically or theoretically speaking requires a certain amount of energy. This, if you do a calculation, you will come across this particular figure of 6 million joules per kilogram. And then when you're trying to convert this iron oxide into iron, you will do so many activities when you will spend energy which cannot be recovered. So in this specific example of recoverable, what I'm talking about is that theoretically speaking, let me emphasize this particular fact that this is theoretically speaking. If you convert iron oxide into iron, you will have to spend 6.1 million joules per kilogram of iron that is produced. Conversely, if you oxidize this particular iron, then you should be able to recover this 6.1 million joules per kilogram of iron that is going to be converted back into iron oxide. So this particular component is what I'm calling it as so-called thermodynamic energy or recoverable energy, which in practice is not exactly recoverable. And at the same time, because conversion requires a lot of other paraphernalia that is needed in order to reduce the iron oxide to iron, that consumes 12 million joules per kilogram of iron produced. Or in other words, if you say what is the embodied energy in iron, or typically my steel, for example, it is somewhere around 18 million joules for every kilogram of steel. So if you're going to use reinforced concrete bars in your steel building for that matter, or angles or trusses or stresses in your steel structure or in your house for that matter, remember it has already consumed 18 million joules for every kilogram of steel that you have in your hand. This is on the lower side, okay? So if you work out the equivalents, concrete, which we use in our buildings, consumes 1.1 million joules per kilogram. And then if you take bricks, they consume 3 million joules per kilogram. In order to make bricks, you have to expend, or you have to spend 3 million joules of energy to get 1 kilogram equivalent of bricks. And if you do these numbers and find out this, you will find that a ceramic tile which is used in the household requires 12 million joules per every kilogram weight of ceramic tile. And if you see sanitary ware which is present in our bathrooms, it is even more energy intensive and it requires 29 million joules per kilogram. And you will see there are plenty of advertisements on the television saying you use the Dulux paint or Asian paints or different brands of paints that are used for painting our houses or exteriors. And if somebody thinks about it, they're extremely energy incentive. Okay, so if you take paint, every kilogram of paint requires 59 million joules. You can see this is almost more than 3 times the amount of energy that is required for making iron. So we have to remember this particular fact that although we paint our buildings, the paints by themselves require so much amount of energy to make them in the first place. And this is the last one which I would like to stress upon. We always talk about renewable energy these days specifically, and we talk about solar cells. And if you see the amount, typically the photovoltaic cells, the amount of energy that is required just to make the photovoltaic cell, let me reiterate or restate that again, just to make the photovoltaic cell, on the lower side, you require 2,500 million joules for every kilogram weight of photovoltaic cells. This is an amazingly large amount of energy that is consumed just to make the solar photovoltaics. I'll come back to this particular point later on. Okay, so that is one concept which all of us as users or designers, civil engineers, electrical engineers, materials engineers, all of us have to remember that there is something called as embodied energy, which is locked up in these particular materials because you are converting or obtaining these materials in the final form that you would like to use from a certain raw material. And converting that raw material into this finished product requires a lot of energy, and that is called as embodied energy. And you have to account for balancing your energy consumption and energy neutralization into consideration. So you have to have this embodied energy as a concept. And the second most important parameter, again, I would like to bring about is what is called as this Harfondal-Heshman index, which in literature generally people call it as HHI. Now this HHI is an absolutely simple concept. It actually tells you, if I want to use simple words, it's the monopolistic tendencies that a particular material has got with respect to availability. So again, this Harfondal-Heshman index, like the embodied energy, is all pervasive. You can use this particular concept of Harfondal-Heshman index anywhere from a pure element like iron to a complex product like a mobile phone, or including even service providing. For example, we have various service providers like Jio, Airtel, Vodafone, and various other service providers. Then you can calculate or you can determine what is called as a Harfondal-Heshman index for looking at criticality or market penetration or free availability, if you want to use any of these words, to attribute to a particular product or a service or a material for that matter. So this is what is called as Harfondal-Heshman index, which is again the second most important parameter that one has to always keep in mind when we were talking about designing, utilizing, whether it is materials or services or products for that matter. And this is a simple formula which actually calculates. A lot of you can actually look at it. It is absolutely simple and very interesting, and it shows the market penetration or how monopolistic this particular product can be. and it reaches a maximum value because of the theoretical way we calculate this particular number or index. It can have a maximum value of 10,000 and it can have a minimum value almost like 0. So what it actually means is that if a particular material or a building or a service has got a very high HHI, then it is a very difficult thing to have. Or in other words, that particular service or a product or a material has got monopoly tendency or restrictive availability tendency for that particular commodity. Okay, so that's extremely important for us to remember when we are talking about designing or developing certain materials. Okay, so these are the two important concepts that I thought we should remember, and I will come back to this particular two concepts when I'm talking about two typical examples. Okay, so what I will talk about is three examples like I told you earlier. One is the buildings, because Shunya is very much involved in buildings, and then the other one is transportation, and I'll come back to the last one, which is again of great interest to Shunya team, that is a solar photovoltaics. So I'll take these three as classical examples, and I'll try to illustrate the role of materials and how they're actually causing or actually resulting in a lot of burden on the environment. What are the different elements or materials that are there which are crucial and which are acting or has a significant effect on the environment, and where we have to look at sustainability as a criteria to change this approach that we have. Okay, so the first one I would like to talk about is bamboo. Now, all of you might say, why are you talking about bamboo? Because as a material scientist, I would like to consider even bamboo as a type of material that is available for our functions. So what I'm showing here is a board or a floorboard. Most of you must have seen this kind of boards, which are used especially in the Western countries for flooring. Or these days, many of the apartments, even in places like Bombay and Bangalore, a lot of construction companies are using these floorboards or wooden boards because they are nice and good for that matter. And these floorboards, which are structural elements which are used in buildings, are made of bamboo. Okay, so there is something nice or interesting to talk about bamboo and the aspect of this being treated as a material for that matter. Now, if you look at this bamboo, this is an absolutely interesting material. It can be used for floorboards. You can take the bamboo and then do a certain amount of processing and convert it into boards, which can be used for structural element like the floors. Or in other words, it can be used as a scaffolding. If you have a concrete structure and you want to do servicing, or you want to build this particular structure, or you want to do some renovation of this particular structure, there are a lot of such scaffolding for which bamboo is used. Absolutely amazing material. Okay. Now, the third example that I came across is this particular building. Okay. This is an absolutely fabulous building, and these structural elements or nice aesthetic looking structures are actually made of bamboo. So bamboo is being used in order to develop this particular resort or a holiday vacation type of a building wherein bamboo is extensively used. So you can use the bamboo anywhere from floorboard to a structural scaffold or a structure which can house something inside, like this elements like a skeleton or this kind of a structure. This is an absolutely interesting material to be considered or talked about, which can be used for housing purposes for that matter. Now, if you look at this, and then if you typically look at, okay, fine, I'm talking about bamboo, and then I'll see what is the global distribution of bamboo. If you see this, this is a very, very tropical crop. And if you see the belt across the globe where bamboo is predominantly grown, then you will find that we are fortunately or luckily one of the countries, or we come in this particular climate belt, which is green, where the conditions of the weather as well as the soil are absolutely perfect in order to grow bamboo or cultivate this particular crop, bamboo. Enough of cultivation. Let's come down to some materials fact or scientific fact about bamboo. Now, if you look at this particular bamboo, then I'm sure it was a surprise to me. I don't know how much of a surprise it will be for a lot of people. It is a grass and not a tree for that matter. Okay, that was quite a surprise for me when I found out about this particular material, bamboo. And its typical harvesting time is anywhere from 4 to 7 years. And mind you, there was a slide I showed you people earlier where wood and non-wood type construction material was also shown as annual consumption figure. Now, if you look at this particular bamboo, 1.4 billion tons of bamboo is consumed every year. This is an amazing number. Okay, so 1.4 billion tons of bamboo is consumed per year, and its lifetime is 4 to 7 years. That is a harvesting time. Then, if you look at, for many people, it will be an interesting fact because they'll be interested in this. If you look at the trade, it's $20 billion in 2020. So annually, the amount of sale or transactions of this 1.4 billion tons is something like $20 billion money-wise is transacted in terms of bamboo alone. Now, if you see who are the main producers of this particular bamboo, it's China, India, and Myanmar are the major producers of bamboo, and about 20 million hectares of land is used to cultivate this particular grass or a variety of grass that is called as bamboo in the world. Now, if you look at some of its structural properties, it has got a tensile strength of 260 to 340, and it has got a certain modulus, which is quite good for rupture as well as elasticity. Now, if you take this and look, this is for those of you who haven't seen, this is how a bamboo forest looks like. There's an absolutely green and nice tall bamboos, grass plants that have grown, and it's a nice view to, or nice place to go around camping or hiking for that matter. Now, if you take this particular bamboo and, like I said, you convert it into a floor board by doing some shredding and converting it into a dense board, it gains a density of 600 to 872 kilograms per square meter, and it has a flexural modulus and the strength and the hardness, and it has got a certain thermal conductivity, and its price of the board is somewhere around $2 per kilogram weight. Okay, so this is the board that you typically come across, which is used for wooden flooring as a structural material, not tiles or cement or concrete flooring for that matter. People are interested in having wooden flooring. So if you look at this, then what happens is there are a lot of people, including people like Shunya team, which is doing a commendable job, that you would like to have a carbon neutral construction. Now, if you think about it, this bamboo flooring is a very nice material to think of as a carbon neutral and a sustainable material for your flooring. Okay. Now, if you typically look at media portrayal of this particular bamboo flooring, media calls it as an income producing crop. There are different types of adjectives that are being used for this particular bamboo. And they call this as poor man's wood, eco-friendly flooring, carbon neutral, galvanizes rural economy, because most of the growth of the bamboo takes place, like I said, it's a grass, and it takes place in quote unquote rural type locations. So these are the typical adjectives with which the media mentions or talks about the bamboo. Then if you say, okay, fine, there's an absolutely good material that you say that it is good for flooring, and it is carbon neutral, and it is sustainable because every year you can cultivate a new crop, use it, and then you can recycle this particular bamboo by taking it back and using it for various purposes after the lifetime is over for that particular structure. How far is it true, or am I just talking in the air for that matter? So these are all the typical concerns that one expresses when I try to advocate somebody to use bamboo flooring. So the concerns is it's a restrictive practice, lack of investment, one of the concerns. And at the same time, this is something which I would like to mention, that there are no building codes if you want to construct a building purely based on wood, or for that matter, bamboo for that matter. So you can see plenty of building codes that are available for steel and concrete to be used, Indian standard codes for that matter. But when you talk about, if you go around looking to say that I want to construct my house purely with wood or bamboo, there are no standardized codes that are actually written. So that is something which is lacking, because of which it becomes a point of concern. Then the biggest question that one would like to ask is it really carbon neutral, and how does it match with the physical properties of materials that we conventionally use, like tiles or slabs or something that we use, or concrete for flooring. So if we want to look at these particular parameters from a materials perspective, then we find that the flexural strength is quite comparable. The flooring that you use with the bamboo is quite comparable to most of the wooden structures that you can have. So it has sufficient mechanical strength to withhold or to hold the weight when it is being used as a flooring material. Then I told you earlier, there is an absolutely interesting concept or an important concept like embodied energy, which has to be kept in mind. And I would say, even though bamboo is a grass, which is a natural grass that is grown, I would like to still use it, because if you want to cultivate this particular bamboo for harvesting it for structural or building purposes, then you have to spend some energy, correct? So if you want to grow a bamboo crop, then if you say, okay, fine, how much is the energy intensity of this bamboo flooring for that matter, then you will say, okay, I have to use water, I have to pump water, I have to irrigate the soil, and I have to take care of this bamboo plantation for 4 to 7 years. I have to have people who are taking care of this particular bamboo plantation. And every time I water the plants, or I sort of provide some manure or do something for the bamboo plantation, I'm indirectly using energy for all these particular activities. Now, if you do an accounting of all those energies which are going into making a bamboo-based flooring, it works out to 15.4 million joules per kilogram of bamboo weight. And then if you say, okay, fine, all these activities of pump running with an electricity, and which in turn produces carbon dioxide somewhere. So if you account for all the emissions related to this particular embodied energy, it works out to 1.41 kilograms per kilogram. Or in other words, every kilogram of bamboo flooring results in emitting 1.4 kilograms of carbon dioxide, which is an important factor for us to consider. Then if you see this carbon dioxide that is emitted or involved in this bamboo process, there are 3 different categories. There is something called as biogenetic carbon dioxide, processing carbon dioxide, and recovery carbon dioxide, various aspects to it. And then there is an economy that is there, wherein it is sold at a price of $5 to $6.50 per square meter, per square foot in USA, and about 30 euros per square meter in Europe. These are the 3 important factors. The first is the environmental part. First 2 are the environmental concerns, that it has a certain amount of embodied energy, which people have to account for, because it's a definite amount of energy that has been spent in making the bamboo flooring. Now, if you do this, and then let's say you compare the embodied energy with respect to conventional materials that are used for flooring purposes. Now, if you see this, very typically the embodied energy per square meter, if you look at it, the bamboo board is about 200 million joules per square meter. You compare this with something like ceramic tile. You see it is 300 to 500 or 600 million joules per square meter. Or in other words, it's almost 3 times higher embodied energy in a ceramic tile compared to bamboo board that you can use. And then if you use something like linoleum or vinyl, remember carpet, and these linoleum, vinyl or carpet are only decorative and they are not structural in nature. Whereas a bamboo board is not only decorative, but it's also structural in nature because it has got a certain load bearing capacity. Now, if you look at that, a vinyl flooring, which we use for decoration purposes, has 300 million joules per square meter. It is non-structural. It is just a decoration. The laminate that we put on our tile or flooring for that matter, it still consumes a great deal of energy, which is much higher than that of the bamboo board. So it immediately tells you that yes, the bamboo board is much better compared to even a carpet, which is a non-structural or non-load bearing element. So in terms of environmental or sustainability perspectives, the bamboo board is absolutely good sense to be used compared to any of these ceramic tiles or stone tiles or these linoleums or vinyls for that matter. Remember, if you use the stone tiles, you can't leave it. These days, we all end up covering it with linoleum or vinyl cover. So everything together adds up, and energy cost is much higher compared to that of the bamboo board. Okay. Now, if you look I mentioned earlier this question of Harfondal-Heshman index or HHI, then I told you this actually talks about market share or market penetration. And if you look at the world statistics, and I've taken the typical statistics that were available to me for the year 2005, the China, India, Myanmar, Nigeria, Sri Lanka, Bangladesh, all these are the different countries that produce bamboo. And if you see this, 78% of the market share is from China. Okay, and the rest of the countries together give rise to about 22%. And this is where it works out to a Harfondal-Heshman index of 6,250 as the Harfondal-Heshman index. Or in other words, now you can see if tomorrow there is a problem because of which China, we are not able to procure or source this particular bamboo from China, then it comes to a crumbling halt. So we can't have any bamboo flooring because 78% of the bamboo that is produced is coming from China. So this is reflected in this HHI, which is a huge number, 6,250, which reflects that there is a material supply constraint or a restriction that is possible for this particular material, bamboo. So although it's a beautiful material to be used from an environmental perspective, in terms of availability, it is concentrated with China, and this is not a very good thing because everybody has to depend on one particular source for this bamboo floorings. So that becomes a bad factor, or we should try to see that the HHI for a particular material is as small as possible. Okay, so that's the negative point of this particular bamboo. It's a very high value. So if we spread, or if other countries like Sri Lanka, India, Myanmar start to cultivate more amount of bamboo, then this HHI becomes smaller, or the availability becomes that much easier without monopolies being present in that particular system. Now, if you see this, if you couple it with what I call as 3 Ps, that is the people, planet, and the prosperity. In terms of planet, the bamboo flooring is carbon neutral. It prevents soil degradation and erosion, and it sequesters carbon dioxide during growth because the bamboo growth requires carbon dioxide as a raw material. And then when you look at it from the point of view of people, then it gives employment to people, or it generates employment, and you don't really need a great deal of education. It just needs a certain amount of skill to be given to the people so that it becomes a sustainable model of employment or revenue earning for a lot of unskilled people. So it's a great positive aspects of this. Now, the only thing that happens is the so-called HHI that I was trying to mention earlier, or trade restrictions, which are limiting as far as this particular material, bamboo, is concerned, if you want to use it for construction purposes or flooring purposes. Now, if you analyze these things, it's an absolutely good material to have bamboo board production because it is carbon neutral, it prevents soil degradation, and then it also sequesters carbon dioxide, which is released into the atmosphere. Then if you see, it has plenty of benefits to be used as a good material for construction or flooring for that matter. Okay, now only negative aspect is the so-called trade restrictions or high Harfondal-Heshman index, or in other words, if you diversify the cultivation of the bamboo crop, then you will have an absolutely good, natural, sustainable material that can be used for construction purposes. Then in the long run, that is also very important for people to remember, is that we have to develop proper building codes so that somebody can build. I know, so if you say, okay, fine, I have to have a structure. If this is the kind of type of construction with a single floor, so much load bearing, with considering the bamboo's property into consideration, there has to be a code that needs to be developed so that people can easily adapt this particular material as a construction material. So this is something which is missing or lacking in the long run, so that people can use this and safely go ahead and start constructing or using this particular bamboo flooring as a housing material for that matter. So if you summarize, or if I summarize, bamboo as a construction material or a material which can be used as part of your housing is an absolutely beautiful, sustainable material, but the restrictions are that you need to cultivate more, and you need to cultivate in different places of the world so that easy availability of material will be there. And at the same time, if there is a parallel development from architects and civil engineers or mechanical engineers for that matter to come out with a building code wherein you define like a concrete or a steel structure that you have absolute building codes like that. If we come out with these building codes, then it will become an absolutely good solution to have sustainable material to be used for construction activities for that matter. Okay, so this is what I had in mind to talk about bamboo. And here I'm showing certain pictures. This is a house. Beautiful picture I came across. It's a carbon 12. This is a glass and timber, of course, not completely bamboo, but bamboo flooring has been used in this particular building, but it is made of glass and timber. And this is a beautiful building which has been constructed wherein people are living in this particular building. Okay, so this is a reality because there are building codes that people have come up with in those particular places wherein they are used. So this is somewhere in the US, a place called Mississippi for that matter. Now there are beautiful examples all across the world that we can adapt or we should use. Now if you see on the left hand side here, this is a building which has been constructed in 2015 in Norway, and it's the world's tallest modern wooden building with 52.8 meters height, and it is 14 floors. Remember, there are 62 flats with 14 floors in this, and it was constructed using a modular prefabricated section wherein there was plenty of wood that was used along with a few other structural elements. Basically, what I am trying to say is there are building codes that are already being developed in several parts of the world wherein people are using wood or a natural element for construction and housing for that matter. On the right hand side here, in another part of the world, this is in Canada, which is a beautiful structure. If you see here, it's a University of British Columbia. It's a hostel, what we call as a hostel. There they call it as a dormitory. It's a 53-meter high dormitory which has been constructed, and it was constructed in just 70 days for students to occupy. There are more than 400 students will move. Of course, now it has been completely operationalized, and this is a building which is made with majority of wood being used in this particular building construction, which is a hostel building with 400 students being occupying this particular university hostel accommodation or dormitory. So there is a lot of construction that is taking place across the world, and it is time that we also use wood and bamboo as a construction material and start developing suitable codes for our country so that we can have buildings made of these particular materials that are there. Okay, so that sort of concludes my part of giving you as a construction material or a housing material bamboo, and of course wood for housing purposes. The next example that I would like to talk about is electric automobiles for transportation. How are we doing with respect to time, Ankita?
Yes, it's already 4 o'clock. So like it would be great if you make it like brief, very short.
Okay, fine. So I will try to keep it as short as possible. Okay, now if you look at automobiles, again, something for a lot of people to think about a great deal. If you look at the statistics, there are 95 million vehicles that are produced in the year 2018 alone. And out of that 95 million, 70 million of these particular vehicles are passenger cars. And then if you look at the carbon dioxide emissions from these cars, 4.6 metric tons per year in driving conditions like US, that accounts to 350 million metric tons of carbon dioxide is emitted every year. Now, the big goal for a lot of people across the world, and everybody is talking about it, is that we want to reduce this carbon dioxide emissions that are coming from these automobiles or vehicles. So as a result, people are advocating electric cars for transportation. Now, if you look at this, there are two important components in an electric vehicle. One is the motor, the other one is the battery pack, which is used for these electric cars. So I'll just talk about these 2 points. Okay, now if you see, there are millions of vehicles that are being projected to be used in these particular coming years. So there are projections about 2030, 250 million vehicles are required for electric transportation. If only 30% of the total vehicles need to be electric, not 100% for that matter. Now, if you break it down to say, okay, fine, what are the different things that are there? There is electric motor and a battery, which are important constituents or configurations. Now, if I break it down and say, okay, fine, I need a motor. These motors require 1.5 kilograms of neodymium, which is a rare earth element to construct these motors, because these are electric motors which require a certain amount of magnetic field to be generated. And the battery that is required is 7.3 kilograms of lithium, because lithium ion batteries is what we are using, or in other words, 0.46 kilograms per kilowatt hour. Okay, for a 16 kilowatt hour battery, you require 7.3 kilograms of lithium is required. And you require about 0.17 to 0.3 kilowatt hours per kilometer for propulsion. And if you compare it with a classical car, the carbon dioxide emissions is about 500 grams per kilowatt hour. We'll come back to this particular thing. So if you look at the global production of this particular element, neodymium, it's 20,000 tons of neodymium is produced, again, by a single country, which reflects the Harfondal Heshman index. And then if you look at lithium, it is a little bit more better, but at the same time, 34,000 tons of lithium is produced per year. Now, if you look for just 8 million cars, I'm not talking about 250 million cars, I'm just talking about 8 million electric cars, they require 12,000 tons of neodymium required per year, and then 58,000 tons of lithium is required per year for making the batteries that go into these 8 million cars. Now, if I put together this particular information, and then I say, what is my embodied energy and emissions, then you find that neodymium, which is an absolutely essential element that is required, one of the elements that is required in the electric motor, it has got an embodied energy of 85 million joules per kilogram, and it emits 5.5 kgs of carbon dioxide per kilogram of neodymium material that is produced, and it requires 55 good clean drinking water or good water for producing this. And then if you compare again, lithium, which is another important element, then it requires 590 million joules per kilogram of lithium to be produced, and it releases 28 kilograms of carbon dioxide to produce this lithium, and it requires 470 liters. And if you put together these particular facts, what you will come across is that emissions, that is carbon dioxide alone, 66 million tons of carbon dioxide will be emitted in order to produce the amount of neodymium that is required to make 8 million cars with our electric cars. And the amount of lithium that is required that will go into the batteries results in producing 340 million tons of carbon dioxide for 8 million cars alone, not 250 million cars. That is what it is. That is the amount of energy that is locked up in just the batteries or lithium. Now, if you see the lithium batteries, if you want to make 7 kgs per kilowatt hour is the carbon dioxide emissions that are there for every kilowatt hour. And then if you add it up, it runs into huge numbers, okay? The 1 kilowatt hour of what is called as an MNC 111 battery, it releases 72 kgs for 1 kilowatt hour. And then it releases also sulfur dioxide, nitrous oxide, and dust, particulate dust into the atmosphere. All these are polluting systems, and it requires 752 liters of water to produce the batteries. Now, if you put together these numbers and then see what happens, then battery weight is 500 kilograms because it requires 1 kilogram for every kilometer to be driven. And the energy intensity of the battery is only 0.6 million joules per kg, but whereas if you look at gasoline or the petrol, it is so much amount of energy is locked up in this particular system. So if you see 10 to the power 12 million joules of energy will be required apart from the energy that is required to make neodymium, the batteries, and the lithium that is required. This is the electricity that is required to run these particular electric vehicles. 10 to the power 12 million joules. And if you add this up, you require something like 10 to the power 10 million joules per year is the typical electricity that is produced per power station, which means 20 to 30 additional power plants are required. Apart from that, if you look at the charging station requirements, it is huge. You have to have, if you say, okay, fine, like a typical petrol car, if you go to the petrol station, you can fill up the petrol within 5 minutes time. And if you say, okay, fine, within 5 minutes, my battery has to be completely charged because that is the amount of time that I'm spending to fill petrol in my car, then you will have to have a charging station that works at 30,000 volts or 30 kilowatts at 1000 amperes. For those of you who deal with electrical engineering, you will know that it's an absolutely dangerous situation to be in when you have a charging station that is running at 1000 amperes and 30 kilowatts. So these are extremely dangerous conditions to have for a charging station. So although people are advocating the electric cars, but when one looks at the actual materials that are required to make the motors as well as batteries that are required to run these electrical cars, and then the amount of energy that is required to run the electrical cars apart from making the electrical cars, then you will ask this question: is this the right way of going about it? Are the battery driven cars be ever energy and emissions neutral for that matter? Then if you look at it, the materials that are used currently in all these technologies are extremely energy intensive and polluting for that matter. So it's extremely difficult. So that is the sum and substance of the automobiles. Now, if you look at similarly the solar photovoltaics, I don't have much time to dwell on this, but most of you probably know this. So if you see this, the non-renewables is constituting very little to the power generation. And if you look specifically at Indian scenario, we are talking about generate or installing capacity of 175 gigawatts by 2022. Whereas the current installed capacity of photovoltaics is only about 100 gigawatts. But we as a country have taken a bold decision to say that we will have 175 gigawatts of installed capacity of solar up by the year 2022. So let's not go into those things, but I'll just give you some of these particular aspects of looking at embodied energy. Now, if you see silicon photovoltaics are majorly silicon. And if you see the amount of energy, it's 2,355 million joules for every kilogram of silicon to be produced, which can be used in photovoltaics. Apart from silicon, there are plenty of other materials like silver, indium, tin, aluminium, and then I'll tell you some more: glass, steel, concrete, and then plastics and copper. All these are used because you want to have a complete solar panel for energy collection. Okay. Now, if you look at all the amount of energy that is required in order to make a complete solar panel, which can convert your solar energy into electrical energy. Remember, all this energy and carbon dioxide equivalent emission you are having before you start converting the solar energy into electrical energy. Just in order to make the solar panels, you will have huge amounts of energy that is required and emissions that are associated with this. So if you look at embodied energy, for 100 gigawatts of installed capacity is 3,350 petajoules, and a petajoule is 10 to the power 15 joules. Or in other words, if you compare with a typical power consumption or power that is generated by a power plant, it's about 10 to the power 10 joules. So which means it's something like 100 or maybe 1,000 extra power plants that are needed to be created in order to produce materials that are required to make solar panels that can ultimately have an installed capacity of 100 gigawatts. Remember, this is an installed capacity, and if you take the capacity factor, you will have 100 gigawatts of installed capacity, which will give you an electricity which is just about 10 or maybe 20 gigawatts of usable electricity is produced by this 100 gigawatts of installed power capacity of solar panels. So this is an extremely energy intensive materials that are used for making these solar photovoltaics. Okay, so one has to think carefully about a lot of these things. And I had another interesting statistic for people to put up. If you say 100 gigawatts of installed capacity and you say 5 acres of land is required for 1 megawatt capacity, for 100 gigawatts, 2,500 to 3,000 square kilometers of land is required just to install this 100 gigawatts of solar photovoltaics, so that you can generate something like 20 gigawatts of electrical energy. Now, if you look at this, this is an absolutely interesting 2,500 to 3,000 square kilometers works out to Delhi plus Bangalore plus Hyderabad approximately. So if you add up the land area of all these three cities, then it comes out to 100 gigawatts of installed capacity, or maximum about 20 gigawatts of electricity to be produced by this 100 gigawatts of installed capacity. In the process, you've used so much amount of land. Okay, so this is something for people to think about. Now, in all this, I will skip most of these things. This you can look. Is it right? The big question that we have to ask is it useful in the short run or in the long run? Is it the right material for us to be using, because silicon has a lot of embodied energy, and of course it has a lot of HHI index for that matter. And at the same time, we have to seriously talk about end of life processing, because these silicon or photovoltaic systems have got a maximum life of 25 years, but people find that after 10 years, the performance degrades very sharply. And more so in the Indian context and in the criticality of materials, where do we stand? Especially when we talk about the power generation and the energy mix of power generation in our country, can we even think of producing silicon that is required for these photovoltaics, especially keeping in mind the energy mix of Indian power generation? And of course, this comes at the end of life processing. So all this actually comes back to me to say that energy development, materials development and selection is an absolutely important concept for us to keep in mind when we talk about sustainability of everything, whether it is materials or anything for that matter, and systems. And when we think of materials, we have to think completely in terms of energy payback, carbon dioxide emissions payback, of course, the financial payback, and most important, reduction in the resource intensity. It should not be a linear way of consuming materials, but it has to be a circular way of consuming materials, or utilizing materials, not exactly consuming materials. So we have to talk in terms of alternate nature-friendly materials. Okay, so I'll stop at this particular point. All of you, thank you very much for your patient listening, and I'm open to any of the questions. Ankita?
Yeah, so thank you so much, sir.
Yeah.
So we are already running out of time.
Yes. So if somebody has some quick comments or questions, I'm open to questions, sir.
So we'll take only one question, sir.
Yeah, sure.
Okay.
Anything that you say.
So there's a question.
Comments.
Yeah. There's a question from Ankush Pujari.
Yes.
That energy mix of Indian power generation.
Yes.
Electrical vehicles will add load on coal-powered plants and will be harmful to environment.
Absolutely.
Is that right?
Absolutely correct. Because that is the point I was trying to say, that the energy mix that we have in our country, we are heavily dependent on coal as the main source of electricity. Now, the point is, if we typically forget about making the batteries and the electric motors for our transportation vehicles, even if we forget about that, and then we typically talk about only running our cars with batteries or electricity vehicles for that matter, the load on these power systems is going to be huge. We have to have a big strategic change in thinking that we have to go from coal to other less polluting means of electricity generation. Absolutely important point. Yes. And that is true not just for transportation, even for photovoltaics for that matter. As long as we talk about importing our solar panels or not manufacturing silicon which is required for silicon photovoltaics in our country, it is probably okay, but it's not really okay in a global sense. But if you say, okay, fine, we want to manufacture our silicon also, which is used for photovoltaics in our own country, then it is extremely energy intensive, or we have to depend heavily on our electricity mix, or in other words, we'll have to draw power from our coal producing power plants, and that will increase pollution. So in a sense, it is probably not a good thing to talk about photovoltaics because the for emissions reduction comes about much later. The first thing that comes about is emissions that is increased because of making the silicon photovoltaics in the first place. Yeah.
Yeah. So thank you so much, sir. I, on the behalf of Team Shunya and the entire fraternity here together, and on my own behalf, extend a very hearty vote of thanks to Professor Satish Vitta for gracing us and sharing with us your findings and opinions. Thank you for taking your time from your busy schedule and all these efforts. We are extremely grateful to you, sir. Thank you so much.
Yeah. Thank you.
And yeah.
Yeah. Thank you very much.
And I'd also like to express our sincere thanks to each and everyone present here for joining us in our first event fest, Sustain, as a part of our team's social awareness program towards sustainable houses. Hope this session was useful. We have provided a feedback link in the chat. Please fill the form and make sure you write your name correctly, as this name will be written in the e-certificate. And e-certificates will only be issued to those who have filled the feedback form. Thank you so much.
Thank you, Ankita.
Hello, sir.
Yes.
Can I ask, express
Sure.
my point?
Sure.
Yes, sir. It was really informative, as I said, as you were telling about to look about on the embodied energy of the materials that we are using for in the name of renewable energy.
Right.
So, in India, with this much of population and now also schemes are being promoted for electric vehicles also have started. So would we be able to afford this solar panels and electric vehicles in future? Because also we see that we have coming on a limit to use our natural resources also. Plus, in a way, we are promoting these mass producing industries, like we are in a way dependent on them, like silicon and glass and all these requires huge industries. So in a way we are promoting and not finding a sustainable way, I think.
Yes, that's correct. But we have to have a balance. See, what happens is most of the times we in India have to take a very careful path towards equipping everybody to have energy consumption. Okay, so it's like a chicken and an egg. We have to have a very balanced approach. And typically, if you're talking about solar photovoltaics for that matter, there is an optimal rate at which you have to keep installing your solar power generation. So if you typically look at it, do some simple calculations. We shouldn't grow at, let's say, 40 or 50% solar generation capacity addition every year, because that proves negative, or it sort of comes back to us because the amount of pollution that you're going to create in order to manufacture silicon is much more than the returns that you will be able to get. Remember, the returns is spread over a long period of time or the lifetime of the photovoltaics, but whereas the energy consumption and emissions takes place within a short time of installing this particular capacity. So that's why we have to work out an optimal level of growth. So it's good to say that I want to have 200 gigawatts or 300 gigawatts on paper, but in practice, we have to have somewhere around 15 to 20% of our electricity mix being substituted with renewables. So that is being given, or rather advised, as a good way to go so that you don't significantly enhance your carbon dioxide emissions by doing this burden. Does it answer your question, Ajay Pawar?
Yes, sir, yes.
So we have to have a balanced approach. We shouldn't go too much on the extreme also.
Yes. And I think it may require some failures in policies and also for reaching to an optimum level in coming future.
So we have to have a balanced or a calculated approach. and wherein, it is involving designs, planning, and execution.
Yes, sir. Yes. And sir, what do you think about indigenous materials using which were in our country we used ancient house making process. We did use indigenous materials for house making, but
Yes,
today today we see the villages are also like half cities only, crowded and full of cements. So
correct.
uh, can we make people accept to turn back to the old ways, and also build houses which are more robust and similar strength like that of Portland cements?
Sure, definitely it is possible. But like I said, when I was talking about bamboo based or wooden based structures that can be used, the problem is we have, like I mentioned during my talk also, we have building codes for concrete and cement. We do not have building codes for our ancient methods of construction. Okay, it's all knowledge or skill based that is going around. So that is where it becomes a responsibility of people like civil engineers and mechanical engineers and various other professions like architects to actually look at ancient methods of construction and then come out with actual building codes which are acceptable to people. Now, if you go with a proper building code and then tell a person, look, I mean, this is the way you have to construct so that you can have a good strength, okay, which can stand for all weathers purposes, people will be willing to accept. Now, if you say tomorrow, I'm going to construct a mud house, and then if you want to sell that particular concept, nobody will buy it because there are no standards or building codes that are written for a mud house, for example.
Yes, yes, sir.
So
Does it answer
adding to
your
it,
question, Ajay Panwar?
Yes, sir. Definitely, we will
So the
require
responsibility
standards.
is for people to write proper building codes looking at these methods.
Yes, sir. Yes, yes, sir. I think that too maybe takes some time, because the process means it's like taking a bigger turn and coming back to the original place. So I think that too
Yes,
maybe.
but the point is, the earlier we do, the better it is.
Yes, sir. Yes. Yes. Thank you very much.
Yeah, thank you. Any other question
good
or a comment
afternoon.
anybody wants to ask?
Yeah, I just wanted to add a few things.
Yes.
Also, thank you. Like, this was really amazing, and it was such an eye opener. I'm not from an engineer background, so I'm a craft enthusiast, and I'm studying craft design. So, when we were talking about bamboo as a material, so I've personally actually experienced how the working is, how the strength is, and I feel as like this is a point I really need to make here, since most of like people here are engineers. That craft sector, we really need you people to come and work in craft sector, because it has a lot of potential. Like after agriculture, if you see, it is employing most like largest sector after agriculture. And when we say about skill based, or when we say about indigenous materials, there's a lot of opportunity in the sector. And I feel we need to build together, like with the engineers, design and craft designer. Then only it can become part of our lifestyle. So yeah.
So Akanksha, I fully agree with you. And that was one of the reasons why in my slides, if you sort of remember what I was trying to
Right.
say, it is
Hmm.
absolutely important for people from all walks of life to come together to make it happen.
Right.
I fully agree with you. And that's why I was making those particular comments. There is investment needed. There is building codes that need to be written. And there is more proper documentation that needs to be done, not just from the point of view of technology, but even crafts for that matter. Yes, I fully agree with you.
Definitely, sir. And also, I feel like when we are getting modernized, or when we are seeing like the Western culture, we are mostly influenced by them. But we have a lot of potential when we say about circular economy, circular this like it was already there in our lifestyle. Like that's the reason why basketry like is still there. It was a part of lifestyle. So I feel in order to sustain such materials and craft, I feel it need to become the part of our livelihood, like the urban lifestyle. And
Yes,
that could be done with a little advancement, not breaking the like the original originality, but advancing the technology or the process, I would say.
Akanksha, I'm fully agreeing with you. I have no qualms about accepting the fact that what you are saying is absolutely correct. And my point, only submission that I would like to make here is that that's where young people like you have to come forward to take this forward. Okay, so people like me are not really going to be there, but at least I want to initiate you people, not just craftspeople, but even engineers and technologists, to start relooking at all these particular concepts.
Definitely, it would be a good way to look ahead, like a craft designers working with engineers and like actually working on roots and bringing up change, because we need to really look into this, into our culture, because that's what our identity is, I would say.
No, Akanksha,
Our culture and craft are our identity, and
I will,
yes.
I will slightly differ from with you on this particular point. See, I don't think we have to talk in terms of ours and yours. The point is, any craft or any technology, the moment it is formalized, it can be for use for everybody for that matter. I'm not very comfortable with the fact that our identity, our culture, yes, we have to take a lot of things from our so-called culture and universalize it.
Right, definitely.
Okay?
Hmm.
Yeah,
Thank you,
any other
sir.
question or comment? Okay, if there are no other questions, Ankita, can I leave now?
Yes, so it was a great session, sir.
Thank
Yeah.
you so much, sir.
Thank you, Vamika, thank you, Jyoti, and thank you, Amita. It was very nice, and thanks for calling me to give this particular talk.
Thank you, sir.
Yeah.